Welcome back to QHSE Talks. Imagine you have a worker who just finished an 8-hour shift.
Okay.
And they were wearing a top-of-the-line, perfectly fit tested respirator the entire day, like the whole time.
Right, doing everything by the book.
Exactly. And the air monitoring pumps in the room, they showed that airborne chemical concentrations never even came close to crossing the legal limits.
So on paper, everything looks great.
Right. By all mathematical and regulatory accounts, that worker had a perfectly safe day. But then 48 hours later, their medical lab work comes back.
Oh, no.
Yeah, and their blood shows a massive, highly toxic overdose of an industrial solvent.
Yep.
So how is that physically or mathematically possible? Where did the system actually fail?
Well, I mean, that scenario right there is the absolute nightmare that keeps occupational health professionals awake at night.
I can imagine.
Because it exposes the hard fact that what we do isn't just, plugging numbers into a spreadsheet. The human body is this highly complex, porous organism.
Yeah, it's not a closed system.
Exactly. And the industrial environments we place those bodies in are just incredibly dynamic.
And navigating that dynamic environment is exactly our mission for this edition of QHSE Talks. So for those of you listening, I'm talking directly to you right now.
The professionals in the field.
Yes, you are an industrial hygienist, a safety professional, or maybe you are deep in the trenches gearing up to conquer the ASP Domain 1 Topic 14 exam section.
Which is a heavy one.
It really is. Today, we are undertaking a comprehensive exploration of occupational exposure assessments. We're taking biological monitoring, chemical limits, threshold limit values, short-term exposure limits, and time-weighted averages.
It's basically a massive alphabet soup.
Totally. And we are translating all of those acronyms from that daunting alphabet soup into a masterful, logical framework.
I think the first step in building that framework is actually breaking down the traditional safety mindset.
What do you mean by traditional?
Well, most of the time when people think of workplace safety, they just picture an OSHA inspector showing up with a clipboard.
Right, checking boxes.
Yeah, they think about regulatory compliance, like, did I cross the line? Yes or no? Am I getting a fine?
Uh-huh.
But industrial hygiene demands a complete paradigm shift. It is the art and science of anticipating, recognizing, evaluating, and controlling workplace hazards to prevent illness, impaired health, or significant discomfort.
I really want to focus on that word, anticipating. It's a proactive discipline.
Very proactive.
We aren't waiting for the worker's blood test to come back toxic. We are trying to predict the physiological future and change the environment before a worker's health is permanently altered.
That's the ultimate goal.
But to do that, to evaluate a hazard properly, we have to know what the finish line looks like, We have to know whose rules we are actually playing by.
Right. And as any CSP candidate knows, there isn't just one rule book.
Far from it. We operate in this landscape of overlapping and honestly sometimes heavily conflicting standards.
Yeah, it gets confusing fast. The most recognizable one, of course, is OSHA's PL.
The permissible exposure limit.
Right. This is the legal, enforceable ceiling set by the Occupational Safety and Health Administration. And it's calculated based on a conventional 8-hour workday and a 40-hour work week.
But the PAL is inherently flawed if you are purely looking for the absolute gold standard of human health, isn't it? I mean, the OSH Act literally forces the agency to consider economic impact.
Yeah, that is a crucial distinction you must understand. It's not just about biology.
Right.
When OSHA wants to set or lower a PEL, they are bound by a legal requirement to demonstrate technical and economic feasibility.
So they can't just say zero exposure is best.
Exactly. They have to analyze an entire industry and ask, hey, if we enforce this strict new limit for airborne silica or beryllium, does the engineering technology even exist to measure it down to that microscopic level on a mass scale?
And if it does exist, is it affordable?
Right. We're requiring that technology bankrupt the entire manufacturing sector. They have to weigh that.
So the PEL isn't just a biological health standard. It's really an economic compromise.
It is.
It's the law, but it's a law that has been negotiated.
Which is why PLLs often lag decades behind the most current toxicological science. I mean, it takes a monumental legal and bureaucratic effort to change them.
That makes sense.
And that brings us to the counterweight in the industry, which is the ACGIH's TLV, or threshold limit value.
The ACGIH being the American Conference of Governmental Industrial Hygienists.
Exactly. And they operate entirely outside of that bureaucratic constraint.
Because they aren't writing laws, right? They're basically writing scientific opinions.
Precisely. Their TLVs are not legally enforceable limits that generate automatic fines from the government.
But they're still super important.
Oh, globally, the TLV is highly respected as the absolute gold standard. You have this ACGIH committee of public health experts, toxicologists, and doctors.
Really smart people.
Yeah, and they review experimental human and animal studies, along with epidemiological industrial experience. And from that, they determine the airborne concentrations, where they believe nearly all workers can be repeatedly exposed day after day over a working lifetime without adverse health effects.
And they update this list annually, right?
Yes, every single year.
So no economic lobbying, no congressional hearings, just raw biological science. But even with that scientific purity, the sources I'm looking at include a very heavy caveat about TLVs.
Yeah, they do.
They explicitly state that a TLV is not a fine line between safe and dangerous.
Right, because the human body is not a standardized machine.
We're all different.
Exactly. We all have different genetics, different liver enzyme functions, pre-existing illnesses, varying body masses.
And lifestyle factors, right? Like smoking or your diet.
All of that plays a role. ACGIH is very clear that while the TLV protects nearly all workers, a small percentage might still experience discomfort, sensitization, or even health issues at concentrations well below the published TLV.
So individual susceptibility is essentially the wild card here.
It absolutely is.
So if I'm looking at this structurally, OSHA's PLL is the absolute speed limit on the highway. Say it's 65 miles per hour. If you go 66, you get a ticket. The ACGIH's TLV is like that yellow diamond warning sign before a sharp curve that recommends a safe speed of 45 miles per hour.
I like that analogy.
You might not get a legal ticket for taking that curve at 55, but the pure physics of your car's traction, the science, dictates that you might just slide off the road and crash.
That perfectly illustrates the difference between legal compliance and actual hazard prevention. You can be perfectly legal under OSHA and still cause an occupational illness because you ignored the TLV.
Wow. Okay, we also see two other major acronyms populating the exposure rule books, NIOSH REL and the WHEEL.
Let's place those in the hierarchy.
Yeah, how do they fit in?
Well, NIOSH, the National Institute for Occupational Safety and Health, sits under the CDC. They act as the research arm.
Okay.
Their REL, or recommended exposure limit, is often the scientific basis that OSHA looks at when they're trying to formulate a new PL.
So they feed into OSHA.
Yes. And one major structural difference to note for exams is that NIHRs are frequently calculated based on up to a 10-hour work shift.
Oh, acknowledging modern industrial scheduling.
Exactly, whereas OSHA and ACGIH primarily base their baselines on a standard 8-hour shift.
And what about WHEELs? The workplace environmental exposure limits.
Those are critical gap fillers. Think about it. Thousands of new chemicals enter the industrial supply chain every single year.
It's impossible to keep up.
OSHA and ACGIH simply cannot evaluate all of them fast enough. So committees of industrial hygiene experts develop wheels for newer or less common chemicals that don't have established guidelines yet.
Just to provide at least a baseline consensus of safety.
Right.
There is one limit that operates completely differently than the rest of these, though. The IDLH.
Immediately dangerous to life or health.
Yeah. When I first heard that term, I assumed it meant a concentration where you literally just drop dead on the spot.
It's a bit more nuanced than immediate fatality, though, that is certainly possible.
So what does it actually mean?
The IDLH was originally developed by NIOSH specifically for respirator selection. It defines an atmospheric concentration of a toxic, corrosive, or asphyxiant substance that poses an immediate threat to life.
Okay.
Or it would cause irreversible or delayed adverse health effects, or, and this is key, would interfere with an individual's ability to escape from a dangerous atmosphere.
Meaning, if a chemical acts as a narcotic and makes you dizzy and confused within 2 minutes, you literally can't find the door to escape.
Exactly. Now, the defining metric of an IDLH value is that it represents a concentration from which a worker could escape without injury or irreversible health effects within a 30-minute window.
If their respiratory protection completely failed...
Right.
Wait, hold on. If I'm a worker and my supplied air respirator gets cut, does that mean I have a 30-minute window to, finish turning off the valves and pack up my tools before I evacuate?
No, absolutely not. Not under any professional interpretation.
Okay.
The 30-minute window is purely a physiological safety margin built into the toxicology calculations.
Yeah.
It is a buffer for catastrophic failure.
So it's not a timer for finishing a job.
The operational reality is that the very second an environment hits an IDLH state, the goal is instantaneous evacuation. Drop everything and run.
Got it. So synthesizing all of this, for the safety professional standing on the factory floor, You have an OSHA PEL telling you one number,
Right.
an ACGIH TLV telling you a stricter number,
Yes.
and maybe a NIOSH RIL floating in the background. If my company policy only dictates OSHA compliance, but the TLV is half that amount, what is my ethical and professional obligation?
The prevailing standard of professional practice dictates the golden rule of industrial hygiene.
Which is?
When faced with conflicting standards, you must adhere to the more stringent standard to hold worker safety paramount.
Always go with the stricter one.
Yes, your mandate is the preservation of human health, not merely protecting the company from regulatory citations.
Right.
I mean, defending an occupational cancer cluster 20 years from now by saying, well, we were under the PEL, that is a profound failure of the profession if the TLV was warning you the whole time.
The science has to lead. All right, we've established the authorities and the baseline philosophy, but how do we actually apply these limits to the chaos of a working day?
That's the real challenge.
Because an air sample is just a single snapshot in time, but a shift is 8 hours long. The hazard breathes, it fluctuates. So how do we measure the entire narrative of a worker's exposure?
We use the foundational metric of the entire discipline, the TWA, or time-weighted average.
Okay.
It averages out the peaks and valleys of airborne contaminants over a conventional 8-hour workday.
My instinct here is to look at the TWA as a massive loophole for employers.
How so?
Well, if the entire evaluation rests on an 8-hour average, couldn't a facility technically expose a worker to a massive choking cloud of toxic gas for 5 minutes and then stick them in a perfectly clean ventilation room for the remaining 7 hours and 55 minutes?
I see where you're going with this.
Because the math would average out to a completely safe, low daily exposure. How does the system prevent that?
You've just identified the fundamental limitation of the TWA. The TWA assumes that the human body, specifically the liver, kidneys, and respiratory system, can efficiently process and recover from small, temporary spikes of a toxic substance,
Assuming the overall day is low.
provided the overall biological burden across the day remains low. But certain chemicals are brutally acute. They cause immediate severe damage.
With burning your lungs.
Exactly. For those chemicals, averaging is mathematically useless and biologically dangerous. That is why the ACGIH created the STEL.
The short-term exposure limit.
Right. The STEL supplements the TWA. It is a strict parallel limit used when a chemical is highly irritating, causes chronic or irreversible tissue damage, or triggers dose-rate-dependent toxic effects.
Like severe narcosis from a massive short-term spike.
Yes.
And the rules surrounding the STEL are incredibly rigid, aren't they? It's not just a secondary number, it has a whole biological clock attached to it.
The criteria are absolute. A STEL is defined as a maximum 15-minute time-weighted average exposure. You cannot exceed the STEL concentration for more than 15 minutes.
Okay, 15 minutes max.
Second, you cannot hit that STEL level more than 4 times in a single workday.
4 times max.
And third, there must be at least 60 minutes between those successive STEL exposures.
Why those specific intervals? I mean, 15 minutes, 4 times, 60 minutes? It seems oddly specific.
It's mapped to human pharmacokinetics. The 15-minute cap prevents the blood concentration from reaching a level that triggers acute systemic failure or local tissue burns.
So it stops the immediate shock.
Right. And the 60-minute gap is the estimated metabolic recovery time. It gives your liver enzymes a chance to process the acute dose and your respiratory system time to clear the irritating gas before you get hit with another spike.
So if you string those spikes together without that 60-minute break,
The body's clearance mechanisms are totally overwhelmed and toxicity compounds exponentially.
that makes profound sense. And then we have the TLVC, the ceiling limit. Where does that fit in?
Well, if STEL's a 15-minute cap, the ceiling is the absolute instantaneous hard stop.
Instantaneous.
It is a concentration that must never be exceeded during any part of the working exposure, not even for a second. We use ceiling limits for substances that act almost instantaneously, like hydrogen chloride or certain fast-acting asphyxiants.
I think we need a conceptual framework here to lock this in for the listeners.
Let's do it.
Think of exposure management like managing an extreme diet.
Yeah.
The TWA is your daily caloric limit. Let's say 2,000 calories.
Okay, 2,000 calories for the day.
You can have a tiny breakfast and a massive dinner, and as long as the total day averages out to 2,000, your metabolism handles it.
The biological burden is distributed over time.
The STEL, however, is a biological governor that prevents you from eating all 2,000 calories of pure refined sugar in a single 15-minute sitting.
Because that would be a disaster.
Right, because even if your daily average meets the rules, that sudden 15-minute spike in glycemic load will trigger an insulin shock and make you violently ill. The The STEL protects against the shock.
And the ceiling limit.
The ceiling limit is an absolute ban on drinking battery acid. It doesn't matter if your daily average of battery acid is very low. It doesn't matter if you only drink it for 2 seconds. You just never cross that line, ever.
That is a highly effective way to conceptualize the different modes of toxicity.
But there is a gap in this system, right?
What's the gap?
What happens if you have a chemical that has an established TWA, but the ACGIH hasn't assigned it a specific STEL or ceiling? Does that mean unlimited spikes are allowed as long as the 8-hour average holds?
The rules for excursion limits cover that loophole.
I knew there was something.
Yes, and this is prime territory for exam questions. For substances without a specific STEL, excursions can exceed 3 times the TLV TWA value for no more than 30 total minutes during a workday.
So a 3x multiplier.
Yes. However, under absolutely no circumstances should an excursion ever exceed 5 times the TLV TWA, even if the 8-hour average remains compliant.
So it basically acts as an artificial STEL and ceiling.
Precisely. It prevents extreme fluctuations of poorly understood chemicals.
Okay, we understand the architecture of the limits. Now we have to translate the theory into practice. We have to do the math.
Time to crunch some numbers.
Because, as an industrial hygienist, you are going to be handed a stack of laboratory reports with varying concentrations and varying times, and you have to synthesize them into a single legally defensible number.
The formula for calculating a time-weighted average is essentially a sum of weighted blocks.
Weighted blocks.
Yeah, you take the concentration of a specific exposure period, multiply it by the duration of that period, and do that for every distinct task throughout the day. Then you sum all those products together and divide by the total hours in the shift.
Let's run a scenario directly from the study materials.
You okay?
We have an employee exposed to carbon monoxide, COO. They spend 1 hour in an area with 100 parts per million. Then they move to a heavier process for 2 hours at 500 ppm.
Okay, 1 hour at 100, 2 hours at 500.
Right. Finally, they spend 15 minutes dealing with a furnace exhaust at 700 ppm.
The very first thing a safety professional must do here, and this is the trap that catches so many on the exam, is normalize the units of time.
Right, because we have hours and minutes mixed together.
We must convert those 15 minutes into hours, which is 15 divided by 60, so 0.25 hours.
Now we build our blocks. Let's do it together.
Go for it.
Block 1 is 100 ppm multiplied by 1 hour, which gives us 100.
Right. And block 2 is 500 ppm multiplied by 2 hours, which gives us 1,000.
And block 3 is 750 ppm multiplied by 0.25 hours, which gives us 187.5.
So now we sum the products. 100 plus 7,000 plus 187.5 equals 2,187.5.
Okay.
Finally, we divide that sum by the total time of the exposure we measured. So 1 hour plus 2 hours plus 0.25 hours is 3.25 total hours.
So 287.5 divided by 3.25 hours.
Which yields a time-weighted average of 396 ppm.
So for that specific 3.25 hour block of their day, their average exposure was 396 ppm, despite hitting that massive 750 ppm peak.
Exactly.
Let's do a full 8-hour shift example, Toluene exposure.
All right, Colleen.
The worker is at 90 ppm for 2 hours, 120 ppm for 1 hour, and 20 ppm for the remaining 5 hours.
The blocks are straightforward. 90 times 2 is 180.
120 times 1 is 120.
And 20 times 5 is 100. The sum is 400.
Then we divide by the total 8 hours.
Right. 400 divided by 8 is a TWA of 50 ppm. And since the allowable TWA limit for toluene is 100 ppm, this exposure is perfectly safe.
But the real world rarely isolates one hazard metric at a time, you know.
Very true.
What happens when a process triggers both TWA and STEL concerns simultaneously?
That's where it gets tricky.
The sources outline a scenario for trichloroethylene degreasing. The worker pulls freshly degreased metal parts out of a hot vat first thing in the morning. For those first 15 minutes, the exposure is intense, like 25 ppm.
Okay.
Then the worker does routine loading for 4.75 hours at 10 ppm and cleanup for 3 hours at 5 ppm.
So as an industrial hygienist, the moment you see a 15-minute high-intensity task, your STEL radar must activate immediately.
Before you even bother calculating the 8-hour average.
Yes. You check the short-term danger first. The source tells us the TLV for trichloroethylene is 50 ppm, and the STEL is 100 ppm.
Their morning spike was 25 ppm, and the STEL limit is 100 ppm.
So the spike is well below the short-term danger zone, and it only lasted 15 minutes, which satisfies the duration rule. The acute hazard is cleared.
Phew, now we evaluate the chronic full-day hazard.
We run the TWA math.
15 minutes is 0.25 hours.
So 25 ppm times 0.25 is 6.25.
10 ppm times 4.75 hours is 47.5.
And 5 ppm times 3 hours is 15.
The sum of all those is 68.75. Divided by the 8-hour shift, we get a TWA of 8.6 ppm.
And with an allowable TLV of 50 ppm, their 8.6 ppm exposure is well controlled.
This multi-layered check is the daily reality of exposure assessment. You have to prove the worker is safe from both the sudden acute shock and the slow chronic buildup.
It's a dual threat analysis.
But here's where the math collides with modern labor practices. Every calculation we've just done assumes a neat, perfect 8-hour shift.
Which is getting rarer these days.
Right. Modern industry runs on 10-hour, 12-hour, or even 14-hour turnarounds. So what fundamentally happens to human biology and our math when a shift extends past 8 hours?
A profound biological shift occurs. When you work a standard 8-hour shift, you have 16 hours away from the facility.
Take rest.
Yes, and that 16-hour window is critical. It is the biological half-life clearance window where your liver, kidneys, and lungs metabolize, filter, and excrete the chemical burden you absorbed.
So when you work a 10-hour shift, you aren't just adding 2 hours of poison to your body.
No, you are simultaneously stealing 2 hours of recovery time from your organ.
Oh, wow, that's a double whammy.
Exactly. You're absorbing the toxicant for longer, and your body has only 14 hours to clear it before you step back onto the factory floor and start absorbing it all over again.
So the baseline chemical load in your bloodstream never returns to zero.
It begins to compound, shift after shift. Because of this compounding biological burden, the allowable concentration in the air must be artificially lowered to protect the worker. You absolutely cannot use the 8-hour PEL for a 10-hour shift.
You have to do an extended shifts adjustment. Yeah. Let's look at the mechanism for that. Say we have an 8-hour PEL for respirable dust set at 20 milligrams per cubic meter, but the facility moves to 10-hour shifts.
The most common derivation mechanism is simple proportions. You take the standard 8-hour PEL, multiply it by 8 to get the total allowable dose unit, and then divide it by the actual hours worked.
So 20 milligrams per cubic meter multiplied by 8 is 160.
Right. Then divide 160 by the 10-hour shift, and your new adjusted PEL is 16 milligrams per cubic meter.
By simply changing the HR schedule, the legal and safe allowable limit drops from 20 down to 16.
And that requires a massive change in ventilation engineering or process control. It demonstrates that time is just as toxic as the chemical itself.
It also highlights why safety professionals must be intimately tied to operations and HR.
Oh, without a doubt.
If a floor manager quietly institutes mandatory 2-hour overtime for a month just to meet production quotas, they might be systematically pushing their entire workforce into chronic overexposure, even if the air monitoring devices read the same concentrations they always have.
It happens all the time.
All right, we've mastered single chemicals and the manipulation of time, but let's escalate the complexity.
Okay.
Walk into a paint formulation plant, a hazardous waste remediation site, or a confined space. Workers are practically never breathing a single isolated chemical.
Rarely ever.
They are breathing a complex stew of vapors. How do we assess exposure when multiple hazards combine inside the human respiratory system?
Well, when you have multiple chemicals in the air, evaluating them individually against their individual PLs is a fatal error.
You can't just check them one by one.
No. You have to assess their combined aggregate effect on the body. We use a specific calculation called the mixture TLV formula.
Conceptually, this formula is about finding the percentage of the biological limit that each chemical consumes, right?
That's a great way to frame it. The formula is the sum of fractions. You take the measured concentration of chemical 1 in the air and divide it by the TLV limit for chemical 1. That gives you a decimal, which is essentially the percentage of the limit you've used up. You repeat that for chemical 2, chemical 3, and so on. Then you add all those fractions together.
If the total sum of all those fractions is greater than 1, meaning you've exceeded 100% of your biological allowance, the mixture TLV is exceeded and the environment is unsafe.
Yes, but there is a massive non-negotiable condition attached to this mathematical tool.
What's the catch?
You cannot just throw any random combination of chemicals into this formula. The physiological effects of the mixture components must be similar. They must target the same organ system.
Break that down. Why does the target organ matter for the math?
Because if you have chemical A, which is a hepatotoxin that exclusively damages the liver, and chemical B, which is an irritant that exclusively causes dermatitis on the skin, their toxicities don't stack on top of each other internally. The liver isn't feeling the burden of the skin irritant. But If you have 3 different organic solvents, say hexane, toluene, and xylene, and they all act as central nervous system depressants, they're all attacking the exact same neurological pathways.
So they're burning compounds.
Yes, that is when you use the mixture formula.
Let's run the walkthrough from the text. We have a worker exposed to 3 different solvents. Heptane has a measured concentration of 425 ppm against a TLV of 1600.
All right.
Methylchloroform is at 270 ppm against a TLV of 1900.
Got it.
And perchloroethylene is at 175 ppm against a TLV of 33.
So we set up our fractions to determine the percentage of allowance used. For heptane, 425 divided by 1600 is 0.27. So heptane is using 27% of our limit.
For methylchloroform, 270 divided by 1900 is 0.14. So it's using 14% of the limit.
And for perchloroethylene, 175 divided by 33 is...
All right, I want to pause on that last one. 175 divided by a limit of 33. That single chemical is already massively over its own individual limit before we even finish the mixture math.
It is already at 5.30, which means 530% of its allowable dose. The environment is already a catastrophic failure.
Yeah, totally failed.
But to complete the mixture assessment, we add the fractions. 0.27 plus 0.14 plus 5.30 equals 5.71.
Converted to a percentage, the worker's central nervous system is experiencing 571% of the allowable combined toxic dose.
It's a severely toxic atmosphere.
The sources also note that this principle of proportionality isn't just for human toxicity. It's used for physical hazard assessments, too.
Like flammability.
Exactly, estimating the lower flammable limit, or LFL, of a mixture. If you have a paint stripper composed of 15% acetone, 20% toluene, 30% methanol, and 35% dichloromethane, you use proportional math to find the composite flammability risk of the vapor cloud.
The exam frequently tests the LFL mixture calculation to ensure you understand that physical hazards compound in the exact same additive way that toxicological hazards do.
But earlier, you mentioned that the mixture formula assumes an additive effect. It assumes that 1 plus 1 equals 2. But biology isn't always linear, is it?
No, it's really not.
What happens when chemicals interact in the body and 1 plus 1 suddenly equals 5?
You are describing the phenomena of synergistic effects, and it is honestly one of the most dangerous and complex areas of industrial hygiene.
Synergism?
Synergism occurs when 2 chemicals interact chemically or biologically to magnify their overall toxicity to a degree far beyond their individual components.
How does that actually happen physiologically? Give me an example of synergism tearing down the math.
A classic physiological example is the relationship between asbestos exposure and cigarette smoking.
Okay.
If you look at a population exposed only to asbestos, their risk of developing lung cancer or mesothelioma increases significantly due to the physical scarring of the lung tissue.
Makes sense.
If you look at a population that only smokes cigarettes, their risk of lung cancer is also highly elevated due to chemical carcinogens.
Sure.
But if you have a worker who smokes and works with asbestos, the risks don't just add together mathematically, they multiply exponentially.
Why? What is the mechanism there?
The respiratory system has these tiny hair-like structures called cilia that constantly sweep debris and foreign particles up and out of the lungs.
Like a biological broom.
Exactly. The toxic chemicals in cigarette smoke paralyze and destroy those cilia. So when the worker inhales the microscopic asbestos fibers, their lungs have lost their primary mechanical defense mechanism.
The broom is gone.
Right. The fibers penetrate deeper, they stay longer, and they cause radically more cellular damage than they would in a non-smoker's lungs. The smoke literally weaponizes the asbestos.
If the math formula of 1 plus 1 equals 2 breaks down during synergism, how does an industrial hygienist establish a safe limit?
You step away from simple formulas. When known synergistic chemicals are present in the workplace, the evaluation process becomes entirely dependent on advanced toxicological data, professional judgment, and heavy coordination with occupational medical physicians.
It's not just a spreadsheet anymore.
No. The baseline TLVs are no longer sufficient guarantees of safety. You often have to drive exposures down to fractions of the TLV or engineer the process to completely separate the synergistic chemicals.
We have been hyper-focused on molecules floating in the air gases, vapors, fumes. But what happens when the hazard has absolutely no mass?
Physical hazards.
Right. When it isn't a chemical at all, but pure physical energy. That completely breaks our chemical TWA math. How do we measure an invisible assault-like noise?
Noise exposure assessment is a fascinating subset of the field because acoustic physics behaves very differently than chemical diffusion. We measure occupational noise in decibels, specifically A-weighted decibels, or dBA.
What does the A weighting do?
The A weighting is essentially an electronic filter on the sound meter that mimics the sensitivity and frequency response of the human ear. It focuses heavily on the mid-range frequencies where human speech and human hearing damage actually occurs.
Let's look at the noise dosage calculation provided in the source outline. We have a worker subjected to 90 dBA for 7 hours, 95 dBA for 45 minutes, and a deafening 100 dBA for 15 minutes.
Much like the chemical mixture formula, noise dosage is calculated as a sum of fractions. The time actually exposed divided by the time legally allowed at that specific decibel level.
Right.
The exam solutions highlight that this specific profile yields an 88% or 119% dose depending on whether you are referencing the 85 dBA hearing conservation action level or the strict 90 dBA permissible exposure limit. But the raw calculation mechanics aren't the most critical takeaway here.
What is?
The relationship between the decibel number and the physical energy destroying the microscopic hair cells in your inner ear. The decibel scale is not linear. It is logarithmic.
Okay, let's break down the physical reality of a logarithmic scale for the listener.
Let's do it.
If I have a chemical exposure of 50 ppm and it goes up to 100 ppm, I have doubled the chemical. It's a 100% increase. How does that translate to noise?
In acoustics, an increase of just 3 decibels under the NIOH standard exchange rate represents a literal doubling of the sound pressure energy hitting the tympanic membrane.
Wait, so if a machine is running at 90 decibels and it gets just slightly louder to 93 decibels, it isn't 3% louder. It is blasting 100% more physical kinetic energy into the worker's ear canal.
Yes. That sheer acoustic power has doubled. OSHA uses a slightly different regulatory exchange rate of 5 decibels to account for intermittent pauses in industrial noise. But the underlying physics are exactly the same.
Wow.
Because the energy compounds so rapidly, a very small increase in decibels results in a massive, precipitous drop in the allowable exposure time.
The sources provide a logarithmic formula to convert a cumulative noise dose back into an equivalent time-weighted average. TWA equals 16.61 times the base 10 logarithm of the dose divided by 100 plus 90.
The constant 16.61 in that formula is the mathematical mechanism that translates the OSHA 5 decibel logarithmic curve into linear time that we can comprehend and manage.
Let's bypass the heavy calculator work and look at the practical reality of the source example.
Sure. Under OSHA regulations, an environment at 90 dBA allows for 8 hours of exposure.
That's the baseline PEO.
But if that noise level goes up to 95 dBA, an increase of just 5 decibels, the allowable safe time doesn't drop by a few minutes. No, it drops all the way to 4 hours. You have cut their safe working time in half.
And if it goes up to 100 dBA,
the safe time drops to 2 hours.
That insight fundamentally changes how you view a factory floor. You can't just glance at a sound level meter, see it fluctuate from 90 to 95 and think, oh, it's just a bit noisier today.
Not at all.
You have instantly decimated the worker's protective timeline. You need immediate administrative controls to pull them out of that room.
Exactly.
Let's transition to the other invisible hazard highlighted in our dive today, respirable particulates. We aren't talking about visible sawdust here. We are talking about microscopic dust.
To understand particulate hazards, you really have to understand the incredible aerodynamic defenses of the human respiratory system.
How does it work?
When you inhale, the air travels through your nose, where turbulence crashes large dust particles into nasal hairs and mucus.
Like a pre-filter.
Yeah. As the air moves down the trachea and bronchi, the passages narrow, and centrifugal force throws medium-sized particles against the sticky mucosal walls.
The body is acting as a series of physical filters.
Exactly. But the exam loves to test on the weakness of this system. What happens to the particles that are too small to be caught by turbulence, but too heavy to behave like a gas?
The outline points to the 1 micron particle as the most dangerous. Why exactly 1 micron? Why isn't a 0.1 micron particle more deadly?
It's a Goldilocks problem of aerodynamics. Particles much larger than 1 micron are caught in the upper airways and expelled. Particles incredibly small, like 0.1 microns or ultrafine nanoparticles, often act almost entirely like a gas.
Meaning they don't settle.
Right. They're so light, they follow the airstreams perfectly, they slow deep into the lungs, but they frequently get exhaled right back out without ever settling.
But the 1 micron particle hits the aerodynamic sweet spot for maximum damage.
It is small enough to bypass every upper airway defense mechanism. It glides perfectly into the deepest, most delicate region of the lungs, the alveoli, the tiny sacs where oxygen transfers into the blood.
Once it gets there.
Once it reaches the still calm air of the alveoli, it is just heavy enough that gravity and physical diffusion cause it to drop out of the airstream and settle permanently onto the delicate lung tissue.
And the body can't sweep it out.
The body has no mechanical way to sweep it out. It just sits there, triggering immune responses, causing inflammation, fibrosis, or turning healthy cells cancerous.
Which brings us to the math of defeating it. Personal protective equipment, specifically respirators. But a respirator isn't a magical force field. We have to mathematically prove it actually works. Tell me about assigned protection factors, or APFs.
Every class of respirator is assigned an APF by OSHA. It's a multiplier that tells you mathematically how much the respirator reduces the ambient concentration of the hazard before it enters the worker's breathing zone.
Let's run the asbestos example from the outline. The OSHA PL for asbestos is 0.1 fibers per cubic centimeter. The worker is wearing a full-face, air-purifying respirator.
The standard APF for a full-face elastomeric respirator is 50. That means the air inside the mask is theoretically 50 times cleaner than the air outside, provided the mask fits perfectly. We use this APF to calculate the maximum use concentration, or MUC.
By multiplying them together.
Right, you multiply the protection factor by the chemical's PE limit.
So 50 multiplied by the 0.1 fiber PL gives us an MUC of 5.0 fibers per cubic centimeter.
That is the hard mathematical ceiling for that specific piece of equipment. If your air sampling shows that the ambient concentration of asbestos in the room is 6.0 fibers per cc, that full-face respirator is legally and mathematically insufficient to protect the worker.
It's failing them.
You must upgrade them to a powered air purifying respirator, a PPR, or a supplied air system, which carry much higher APFs of 1,000 or 10,000.
All of this incredible math, the TWAs, the mixtures, the noise logs, the APFs, it all relies on one massive assumption. It assumes that the number we plug into the formula is accurate. How do we actually capture that number? How do we trap the chemical and measure the physical reality of the factory floor?
We rely on the American Industrial Hygiene Association's 9-step exposure assessment model. It's a cyclical, continuous improvement strategy.
What are the steps?
The steps include establishing a basic characterization of the workplace, assessing exposures, gathering data, evaluating that data against the TLVs and PLs we discussed, and constantly reassessing as processes change.
I want to zoom in on the first step, characterizing the workplace. When a novice thinks of air sampling, they picture walking up to a guy on an assembly line who is doing the same predictable motion over and over and clipping a badge to him.
And that is a fundamental error in hazard recognition. Routine tasks are rarely the source of catastrophic exposure spikes.
Why is that?
Because the facility's engineering controls, the local exhaust ventilation hoods, the sealed vats, the automated conveyors, were specifically designed and balanced to manage that exact routine process.
The danger lives in the deviations.
The real danger, where industrial hygienists find the most egregious and life-threatening overexposures, is in non-routine maintenance.
Like what?
A sealed pipe gets clogged with toxic sludge. The ventilation is turned off. A worker has to open the flange, stick their head inside, and manually chisel it out. Or a welder comes in to repair a tank that used to hold highly flammable solvents.
These activities completely bypass the designed controls.
Characterizing the workplace requires you to interrogate the maintenance logs and interview the floor workers to hunt down these hidden periodic tasks.
Once you isolate the task and the worker, what physical instruments do you use to capture the hazard? The sources contrast two specific technologies, diffusion tubes and vapor monitor badges.
Diffusion tubes, frequently called colorimetric detector tubes, are essentially chemical litmus tests inside a sealed glass tube.
How do they work?
The tube is packed with a specific chemical reagent. You snap the glass ends off, insert it into a calibrated hand pump, and draw a precise volume of workplace air through it.
And the air reacts with the reagent inside.
It causes a colorimetric stain. The chemical reaction turns the white powder brown, or the blue powder pink. The length of that discoloration corresponds to scale markings printed on the glass, giving you a direct reading in parts per million.
That's super fast.
You can also get long-term diffusion tubes that passively draw air in over an 8-hour shift. To find the TWA, you just divide the final scale value by the total hours sampled.
They seem brilliant for immediate field screening. You don't have to wait 2 weeks for a lab report to know if the room is deadly right now. But what is their weakness?
Precision and cross-sensitivity. They have a fairly wide margin of error, sometimes plus or minus 25%, and occasionally A similar chemical in the air can trick the reagent into changing color, giving a false high reading.
So they aren't perfect.
For rigorous, legally defensible, highly accurate compliance monitoring over a full shift, professionals utilize vapor monitor badges.
These are the little plastic discs you see clipped to a worker's lapel, sitting directly in their breathing zone.
Yes. They are passive dosimeters. They don't use mechanical pumps. They rely purely on Fick's law of diffusion, the natural physical tendency of gas molecules to move from an area of high concentration in the room to an area of low concentration inside the badge.
So it just flows in naturally.
The gas diffuses through a porous membrane and binds chemically to a collection media, usually a bed of activated charcoal.
And then you send it to a laboratory where they use gas chromatography to rip the chemicals off the charcoal and weigh them with extreme precision.
Yes, and it gives you a highly accurate 8-hour TWA or a 15-minute STEL.
But there has to be a catch.
Well, because they rely on natural physics rather than a forced air pump, badges have critical environmental vulnerabilities. They're highly sensitive to air velocity.
You mean wind?
Yes. If a worker is standing in a dead air zone with zero wind, a boundary layer of clean air forms immediately over the badge's membrane, starving it of the chemical and yielding a falsely low reading.
What about high wind?
Conversely, extremely high winds can force excess chemical into the badge. They are also vulnerable to high humidity, where water vapor can saturate the charcoal pores and physically block the toxic solvent from binding.
So a great industrial hygienist doesn't just know how to turn the instrument on. They know the physics of why the instrument might be lying to them based on ambient weather conditions.
Exactly. You have to understand the mechanism of the tool, not just the readout.
Which brings us to the final and perhaps most unnerving concept in the source materials.
The blind spot.
Every single piece of math, every badge, every detector tube we have discussed today measures air. It measures what the worker is breathing. But what happens when the hazard circumvents the respiratory system completely?
This is a catastrophic blind spot for amateur safety programs. They spend their entire budget on state-of-the-art air monitoring, they ensure the air is pristine, and they declare the facility perfectly safe.
Right.
But they fail to check the ACGIH TLV booklet for a very specific warning attached to nearly 25% of all listed chemicals, the skin notation.
1 out of every 4 chemicals on that list has a skin notation. What does that actually mean physiologically?
It means the chemical is highly lipid-soluble or possesses properties that allow it to easily penetrate and be absorbed directly through the intact dermal layer, mucous membranes, or eyes, and enter the systemic bloodstream.
Just right through the skin.
If chemical carries a skin notation, relying solely on air sampling is fundamentally flawed and legally negligent.
Because I could have my worker in a hermetically sealed positive pressure suit breathing hospital-grade filtered air, but if they take their glove off and accidentally spill a cup of that solvent on their bare forearm,
their internal organs are still going to receive a massive, potentially lethal toxic dose, and the air monitor on their collar will read exactly 0.
The air monitor captures absolutely nothing, so how do we evaluate that exposure?
We have to bypass the environment and look directly inside the human body. We use biological monitoring, specifically biological exposure indices, or BEIs.
This bridges industrial hygiene directly into occupational medicine.
Yes. A BEI involves taking biological media from the worker blood draws, urine samples, exhaled breath analysis, or even hair and nail clippings, and analyzing them in a clinical lab to find the chemical itself or the specific metabolic breakdown products of that chemical.
To clarify the conceptual difference for the exam and for field practice, air monitoring measures the potential exposure. It quantifies the threat hovering around the worker's body.
Correct.
But a biological exposure index measures the actual absorbed dose. It proves exactly how much of that chemical successfully defeated the ventilation, bypassed the PPE, crossed the skin or alveolar barriers, and is currently circulating through the worker's internal organs.
That distinction, potential exposure versus actual dose, is the absolute core of biological monitoring. The sources provide a brilliant, holistic scenario that ties all these assessment concepts together into a real-world detective story.
Walk us through it.
An industrial facility has a group of workers who perform a specific task. Let's call it a similar exposure group. During routine annual medical surveillance, the occupational health physician runs blood work. The results come back, and several workers in this specific group show significantly elevated levels of lead in their blood. The BEI is flashing a massive red warning light.
The actual dose inside their bodies is way too high.
The hygienist immediately investigates. They pull the historical air sampling data for the entire facility. The data reveals that during one highly specific task, grinding the paint off a localized lead component, the airborne concentration of lead dust spikes heavily.
So they have identified the potential exposure source.
Yes, but is that the actual cause of the high blood levels? To prove it, the hygienist does comparative biological testing. They check the blood lead levels of the other factory workers who operate in the same building, but do not perform that grinding task.
And what do they find?
Those workers' blood levels are perfectly normal.
It isolates the variable. By cross-referencing the biological blood work, the actual dose, with the task-specific air monitoring, the potential exposure, the hygienist pinpoints the exact mechanical failure in the facility.
The controls at the grinding station are failing, or the workers' respirators are inadequate or not being worn correctly. Armed with irrefutable biological proof, the hygienist can walk into the plant manager's office and justify the capital expense to implement an engineering control.
Like a custom-built local exhaust ventilation hood directly over the grinding wheel.
Exactly, to eliminate the dust before it ever reaches the breathing zone.
That is the entire philosophy of industrial hygiene working in perfect harmony. Anticipate, recognize, evaluate, control. The air monitoring provided the theory, the blood work provided the physiological proof, and the engineering control provided the permanent solution.
It perfectly illustrates why this field requires you to integrate so many disparate streams of data chemistry, physics, biology, and engineering, just to protect human life.
And that brings us full circle to you, the listener. Whether you're prepping for the ASP exam or actively managing exposures in a chemical plant, we have covered a staggering amount of technical ground in this edition of QHSE Talks.
We've navigated the bureaucratic friction between OSHA's economic PLs and ACGIH's strictly scientific TLVs.
We've unpacked the rigid physiological rules of the 15-minute STEL and conceptualized the compounding biological burden that makes adjusting TWAs for 10-hour shifts so critical.
We've explored the dangerous multiplying reality of synergistic chemicals,
The logarithmic acoustic physics of noise dosage,
the terrifying aerodynamics of the 1-micron particulate,
and the vital life-saving importance of recognizing the skin notation and utilizing biological monitoring.
You now possess not just the formulas, but the underlying mechanisms, the why, and the how-to master domain 1 topic 14.
But before we go, we must remind you of the ultimate endpoint. The goal of all this complex math, the air sampling and the blood testing, is not merely to document the hazard. The goal is the hierarchy of control.
We must always strive for the safe place paradigm. We want to use rigorous engineering controls to eliminate the hazard at the source or capture it along the air pathway long before we ever surrender and rely on the safe person approach of just slapping a respirator on the worker's face.
Measure it so you can engineer it out of existence. I love that. Which leaves me with one final provocative thought to ponder as we close out.
What's that?
We talked extensively about biological monitoring testing a worker's urine or blood once a year or once a month to check the actual dose inside their body. It is a vital tool, but it is fundamentally a lagging indicator. You are finding out about the overdose after the damage has already started.
That's true.
But biometric technology is advancing at blinding speed.
Right.
Wearables, continuous sweat sensors, transdermal monitors, they are becoming cheaper and exponentially more accurate.
The implications for occupational health are staggering.
Will the annual blood draw be replaced by a smartwatch issued by the safety department? Imagine a biometric wearable that analyzes your sweat in real time, and the precise second your internal physiological dose of a toxic solvent hits the TLV limit, the watch vibrates and alerts you, hey, evacuate the area, your liver capacity has reached maximum safe load.
It would be the absolute pinnacle of personalized, proactive workplace safety.
But how does that level of intimate, real-time biological surveillance interact with a worker's medical privacy? Who owns that physiological data minute by minute? The worker, the corporate HR department, or OSHA?
It's a collision of ultimate life-saving safety and ultimate privacy that the next generation of industrial hygienists is going to have to navigate.
Something to chew on. Conclude this edition of QHSE Talks.